for joining. First thing we wanted to do was to introduce the Allotrope Simple Models to you. So we've talked a lot about these. You've probably heard a lot of different communications, but what are they and why have we created them? Next slide. So the ASM really came out of a working group that was put together by the board of directors in 2020 that was convened to understand how we could really facilitate a better end-to-end workflow, how we can take data and have it be systematized and standardized across the entire data lifecycle, and really looking at that in one particular domain, which is around liquid chromatography, which is our most mature domain of uh, of our Allotrope products at the moment. And so really understanding what are the pieces that we need to be able to go from start to finish. And in doing that, we understood that we had a lot of different pieces, but the pieces that we had there were some gaps that we wanted to be able to fill, and really focusing around two areas. One is to make it easier to adopt the Allotrope products. So there was some feedback that the ADF and the Allotrope data models required a lot of upfront expertise to really be able to integrate into into your organization's tools and software. And also recognizing that the world of data science is changing, and it's changing very rapidly and quite remarkably from where we started, a decade ago. And data science itself has really come into its own as a new field, and really getting the data that we have in all of these different laboratory techniques into a way that's easy for folks that are going to be working on this data to consume in a standardized manner was really, one of the large driving points here. And so what we wanted to do was to develop a companion that sits alongside the existing products that we have with our Allotrope data format, our ADF, and our Allotrope data models that are the semantically linked sort of graph or tabular based models that we've been talking about for a long time. But was there a way to make it very easy for folks to be able to access those that might work in these more generalized situations, or in these areas where the data itself might be sufficient to have a simpler representation of just the core results that we would need to be able to work on that data and to understand it. And so really looking at a method that would be easy to create by software engineers, so really didn't require any particular domain knowledge. The software engineer that's going to be implementing this doesn't need to be a chromatography expert, doesn't need to be an expert in knowledge management and semantic relationships. Also, to make it easy to consume by data scientists. And the data science world has really congregated around a lot of programming languages that are somewhat different than the traditional enterprise languages, where in the past folks would do a lot of things in Java and C Sharp, C++, Objective-C. A lot of data science really revolves around languages like R and Julia and Go and Python. And so to make a way that this data could be consumed not just in a single language, but in many languages was really key. Something that's easy to visualize, something where you can open up that data file and even a human can look at it and read it and say, okay, I know what this data is. I can see my data there. I can see my sample identifier, right there in the file. And as I said before, something that's really easy to access across many different languages. But we still wanted to retain the core advantages of our ongoing efforts. So we wanted to make sure that the terminologies that we just spoke about yesterday were really front and center in what we did what we did with ASM. Wanted to make sure that we're building off the same building blocks that we are for our other tools and our other products like ADM and ADF. And so we wanted something that didn't just reuse those pieces, but used the same structures and was bidirectionally compatible, so it could coexist with ADM and ADF. So the choice to sort of, use AFO and ADM and ADF versus AFO and ASM, there's multiple paths in between those two. So it's not choosing one cuts you off from the other or vice versa. Next slide, please, Jamie. And so ultimately, what we see the Allotrope ecosystem looking like today is we see the ASM is sitting alongside the existing products that we have. We talked a lot about the Allotrope and Foundation ontologies. They are then used in Allotrope data models. We've spoken a lot about those in other Connect meetings about how modeling works, and modeling is still ongoing. It's really being driven by folks in our member organizations that have a need for a specific model. But we won't speak too much about that today, but those are still there. Those can still be used. And the the system that we use that uses RDF based off of an HDF5 file that uses the ADF, that's all still in play and really appropriate for what we think are the more complex use cases. What we wanted to do was to add a parallel workflow here that uses the ASM. That's really just a text file that's simple to understand, simple to use, that can be incorporated very quickly, either to get your folks in your organization on board with Allotrope in the standards that we have, or to make it easier to consume that data downstream. And so I mentioned, it's building off of all the different pieces that we already have in place. Next slide, Jamie. And the pieces that we have in place are really very substantial. So if you haven't taken a look at our website lately, you should go and do that. So allotrope.org, you can go and look at the product releases page, and it lists all the different domains that we've covered in Allotrope. And I want to stress, these are not us going out and trying to boil the oceans. These are all domains that folks are using in their companies that have come to Allotrope and said, hey, this is a key important piece of data for us, and we want to make sure that we have a model that works with all the other data that we have and all the other models that we have in Allotrope. And so we have almost 50 of them here. Some of them are in development, but a lot of them are ready for use and are in our recommended status, right, where they're sort of the gold standard, if you will, of that domain model. And all of the ones here that are tabular models, which is the vast majority of them, they can all be translated into ASMs. And so everything that you're going to see today, the product team working with our vendors have already translated all of these models into these ASM schemas, these JSON files that are ready to go and ready to be used, really today. So why don't we go ahead and keep moving on? And so Amnon Patashik, Allotrope's Technical Director, is going to introduce us to Allotrope Simple Models.
Hello, everyone. I'm going to give a very short brief of the ASM, and the next slide will start with a quick reminder. So yesterday we discussed the need for a data-centric environment where FAIR provide the principle and the data standardization provide the blueprint to a solution. We covered the need for a context. We define the vocabulary, we classify the taxonomy, and we create the ontology, and this is the AFO. And we discussed that this is the basic building block for a data-centric environment, but we need also, it's not enough the context, we need also a structure, which are data models that are blueprint for describing your use case. And finally, we need a standard representation of the structured data. So this is the structure and the format of what we're going to cover today. Next slide. So just a reminder, the AFO was built upon the modular approach of the OVO Foundation. It has the taxonomy, the Allotrope framework taxonomy that classify all the terms. And it's very important to understand that those terms are assigned a unique IRI, a unique identifier. And this uniqueness enabled us to create a JSON format, since the JSON format requires that every element has a key which is unique. So we'll see how we take advantage of it within the ASM solution. Next slide. So practically the ASM leveraged the JSON standard, which is a preferred data format for many scientists that works with almost any programming language and a very rich library of tools. It's both human and machine readable, and it's easily applied for many use cases as we see our the growth in our modeling working group. During the summer, we executed the ASM Transformation tool RFP, which allowed us to make a bidirectional transformation between the JSON representation and the RDF representation. So we have a full set of tools with a round trip. We can go back and forth from ADM to ASM and from ASM to ADM, both of the schema which we'll discuss in a moment, and on the instance data. Next slide. So it is important to remember that ASM is built on the intuitive tabular approach. And what does it mean, a tabular approach? It's a set of key value pairs, practically a table where the keys describe the type of values that are represented in the model, and the keys are those unique pref label that are taken from the ontology, and they ensure the consistency of the solution. Consistency means that whether you are modeling fluorescence or luminance, you are using the same terms across models. These tabular models are easily extended to allow aggregation of a related piece of data. So similar facets, a collection of facets or index information are unified under the same context and represented by the JSON tree structure. And we see here an example, a pick list. There's a pick 1, pick 2, and each pick have a similar collection of facets, description, and retention time. Now, the workflow for creating a tabular model is handled by a tool which we are using, and this is a very simple Excel tool. Next slide. So we have the Excel spreadsheet, which is almost do-it-yourself. And just recently, we had a new model that we gave to the user of the use case, the spreadsheet, and a video that Ben recorded and described how he's populating the spreadsheet. And he just described the model using do-it-yourself. Just watch the video and do it yourself. But there are many cases that the model is a little bit more complicated, such as aggregation. It's not complicated, but it's more detailed. So we have within the Excel spreadsheet the main sheet, which is the metadata sheet, which includes most of the information of the model. We have the hierarchy sheet, which describes the parents-child association or relations. In the case of aggregation, we have the data cube description, the independent model variables, which is the cube dimension, the cube measurement, any restriction, and a sample data set for a data cube. So this is a very simple tool that can be downloaded, or we can send it to any one that wants to create a model, and he can start modeling right away. Next slide. So the ASM model is really simple. And here is just a snapshot of the Excel spreadsheet of the conductivity ASM. As we can see, it's a table. It's a table with the parameter pref label and a sample of parameter value and the unique symbol, which is usually a QUDT symbol. So we have here a measurement identifier and measurement time and analyst, and the values of measurement time is 2015, September, and so on. And the result is conductivity, the value of the conductivity, 273,000 Siemens per meter, and temperature 28.6 with the unit degree Celsius. So this is the Excel spreadsheet to model the conductivity ASM, and we'll see the same reflection of the table in the next slide, which is the JSON document. Next slide. So you see it's almost one-to-one, key value pair, unique keys required in JSON document, and those uniqueness is coming from the fact that we are using pref label in the AFO, in our ontology. So you see the same table, key value is the equipment serial number and the value, and the temperature key value per 28.6 degree Celsius. There are some elements of annotation. For example, those annotations starts with $sign. For example, if we want to include a comment, so here we see a comment, conductivity ASM, and there is one important annotation, which is the manifest, and it's just one element that provides some references, including the identifier of the model, the ontology version that we're using, so the vocabulary version that is in use, and the JSON schema for validation. So how do we validate this data instance, this ASM document? We are using a JSON schema. Next slide, and we'll see the structure of the JSON schema. So to ensure consistency, all the ASM can be easily machine validated using the standardized JSON schema approach. And if you want to read about the JSON schema, it's jsonschema.org. But we created a very modular, a very practical approach for the JSON schema. So first of all, we have a family of technique-specific schema. Those are domain-specific rules that includes constraints that are relevant to a specific technique. So we have a Raman schema, FTIR schema, qPCR, and so on, LCUV schema. So for every technique, we have a schema, but we are excluding from the schema reusable and domain-independent rule and constraint that can be applied across multiple set of ASM. So they are referencing to core schema. Those core schema, as I said, they include the domain-independent rules. And we have some other reusable schemas, such as unit and data cube schema. There are two versions that I'll point out in a moment. There are one that is called the embedded one, and the one that is called just the technique schema, which the embedded one includes the core component already inside. It is embedded for ease of use, and the one that is decomposed into the structure that you see in the drawing, the technique and the reusable constraints. Next slide. So the ASM has a consistent representation of the different models and techniques, which means we gain a consistency that, as we mentioned, that we are using the terms from the AFO, and whether it's fluorescence or luminance, the same elements goes across the techniques, and they can be associated, and in inference application will identify the consistency between the different terms. Aggregated information and index information are well defined, and they are like a tree, like a JSON structure. The definition of data cubes is borrowed from the W3C definition. So you see in the chart below, there is a JSON section within the ASM that describes just the structure of multi-dimensional array. So there is a label, a structure, which include the dimension, the independent variables of the data cube, and the measurement. So we have the label, that structure, and the value themselves in a data set. So there is a very well-defined structure following the W3C for data cubes. And in many cases, we have binary data as a result, such as images. Those binary components are referenced outside the JSON document, outside the ASM, and we are using those intuitive references, such as web URL for binary data that is on the internet location, or if it's locally in the same directory or in a reference directory using a POSIX path, and there are some other references. Next slide. So how do we validate the data instance, the ASM data instance? Very simple. We are not having a specific allotrope tools like we had previously for validation when we used the shackle for validation. We're using off-the-shelf tools and off-the-shelf software packages. There are different versions of the JSON schema. Again, you can view those tools. There is a summary of tools on the jsonSchema.org. So you apply your JSON schema validators, and the input are the schema, for example, here the Raman schema, either the embedded one that I mentioned or the one that is that have references to the core and the reusable schemas, and you input your data instance, and you turn on the validator, and the validator will check that the data instance is passing the requirements and the constraints. And if it's not passing, it will give a list of errors to be corrected. And it is possible to operate the schema validator not on the entire document, but on a subsection of the ASM document, which in many cases will increase the efficiency. Next slide. To summarize, the ASM is really community-driven. It's not just driven by a single vendor or a single company. It's using the allotrope ontologies, the AFO for consistent nomenclature across the technique. We can go back and forth to the ADM, which is more semantically rich representation. So you can start with the ASM, the tabular model, and then if you decide to go into the RDF and the more semantically rich, you can go back and forth. They are compatible. And it builds, as we mentioned, on JSON, which makes it very easy to work with and easy to validate. No more complicated XML parsers, namespaces, definitions, and off-the-shelf tools that are available on the internet without any specific tools that developed by our community. Next slide. So we have a white paper coming soon, and the white paper compares the different alternative between ASM, Animal, and JCamp. And just the highlight, it talks about the format, comparing JSON to the XML and the ASCII that is used by JCamp. It talks about the advantage of the performance of using JSON as your underlying technology. The ease of use that is presented by using JSON, both readable, the format is both readable by computers and humans, very, very clean and very clear. The coverage is growing, unlike the other organizations or initiatives. We are having a large number of models that is growing, and we have in the pipeline already, I think, like more than 15 models in the modeling working group. It is consistent since we have a very consistent use of the unique IRI within the ontology. And we have a very active community that is driving all those requirements and the modeling. Next slide. So we get, very often we get a question, where are the ASM artifacts? So there was a debate at the beginning of the construction of the GitLab repository, whether to categorize the different artifacts under the type of artifacts or the type of, or the technique. And the decision was that to divide the artifacts under the type. So once you go through one example, and I'm giving here one example of conductivity, once you go through one example, you understand it all. So there is a parent location on the GitLab repository, which is the Perl directory. And under the directory, there are different type of subdirectories that are divided by the type of artifact. So we have the subdirectory for the models, for the schema, for the manifest. And under each subdirectory, we have a list of techniques. So it's the type of artifact and then a subfolder, which is a list of techniques. And then under the list of techniques, there is subfolders for the that present the maturity level and the date that it was the model was either drafted or recommended or under a candidate release. So if we go through one example of conductivity models, we have the Excel spreadsheet under the diagram folder, and then we have this the JSON schema for the conductivity under the JSON schema folder, the reusable ASM schemas such as core and QUDT under the same JSON schema folder, and the manifest is under the manifest folder, and the example for data instance is under the test folder. Once you go through a single example, you know it all. Next slide. So you want to start with modeling your use case. So you prioritize the set of the models that you want to submit for governance. You submit it using the Excel spreadsheet. Either we fill the spreadsheet or you can do it yourself. It goes through governance. We are filling the spreadsheet with missing terms in the ontology if we are missing some of the terms. And then we are enriching it by generating new terms and enriching the existing AFO. Then within the governance, we produce the related ADM from the Excel spreadsheet. We have the tool, and the ADM is described, it is defined using RDF format, and it's defined the shackle file and the data instance in RDF. And then we have a set of automation tools that we mentioned. That was the result of this ASM Transformation tool project during the summer. We automatically produce the ASM, both the schema and the data instance. And then you have a complete set of artifacts that I just mentioned a slide earlier for validation and for testing, and you can use it within your use case. So next slide. So this is some advertisement. You need to create a new model for your use case. Join the modeling working group. Every Wednesday we meet at 8 a.m. Pacific time, 11 a.m. Eastern Standard Time. We are discussing the different tabular models. We have all the set of tools to create the schema and the data instance. It is really a streamlined process. We are going to improve it even more. Just bring your use case and we can model it. Next slide.
Great, thank you, Amnon. All right. Well, in the interest of time, let's go ahead and keep moving. So now we're going to turn it over to Ben Wolford-Lim, who's our senior developer at Allotrope, who's going to show a quick demo of what the ASMs actually look like.
Okay, so yeah, so we've talked about ASMs, kind of, where they came from, how they work, how they were built, but what do they actually look like? So we'll just do a little demo of what they look like and how you might use them. Right, so we've discussed the principles, as I said, but we'll take just a quick dive into a file to see how simple it really is. We're saying it's easy. Let's put our money where our mouth is. So for a little context, going back to Corey's earlier comment, typically data scientists scientific researchers, people working with data to sort of explore the content of the data, like to use languages like Python, tools like Jupyter Notebooks. That they're pretty commonplace. So in order to make this kind of a useful and fairly realistic example from that standpoint, we've put together a Jupyter Notebook to look into an ASM, see how it works, and kind of give a little bit of flavor of what you can do with it, and to consider it the proverbial pot of gold at the end of the rainbow. Thanks, Vinny. This is a glimpse into the value that can be created when we start to create these ASMs at scale. If you have all of your data or most of your data in this kind of ASM format, then the reason for the journey together should hopefully become obvious when you see just how easy it is to use that data. So with that in mind, we'll just jump straight into a live demo. It's a Jupyter Notebook. It's going to read, plot, and validate a liquid chromatography ASM file. For those who want to give it a try, if you're interested in data science, the example notebook is available on our GitLab repository. The link is available in the slide deck, which will be shared after the conference ends. I could also paste it into the chat if people are interested in trying to follow along now. Or I can try to copy it into the chat, but of course in presentation mode that won't work, so maybe someone else can copy into the chat, and I'll just jump straight into the demo then. So hopefully it's actually showing the Jupyter Notebook now. Again, I'm never quite confident with these video conferencing tools that they're doing what they say they do.
That's great.
Wonderful. So yeah, this is a Jupyter Notebook. Again, for those who know data science, you probably have seen hundreds of these. For those who haven't, it's just a useful way of representing sort of text, data, images all in one file. You can literally run the code as you go, so you can very easily kind of put together, almost self-actuating reports in some regards. And it's a very common tool for data scientists amongst other users to sort of work with data. So first off, you can see that, as it's structured as an example. So there's text, there's also bits of code which we can run as we go. And first off, we'll run this bit of code, which is literally just pulling down the dependencies that you need to run this, and also doing some setup of a nice, pretty way of printing the data. I'll add for context that this chunk of code here is probably the largest single piece of code in the entire file. And this is just to make it look pretty. So that maybe gives you some indication as to how easy it really is to work with this. And I also have to say thanks to Corey for producing this, because he's the Python programmer. I just kind of put together the framework. He cleaned it up and made it all look pretty. But as I said, you can run it in place. So if I hit the run button, what this does is pull down the dependencies, the things that you need. For context, for those who are familiar with data science and use this regularly, all of these are standard Anaconda includes. So I have an Anaconda installation, and all of this was already in place. I didn't have to download a single thing. Easy to run. So loads it up, just sets up a nice little tool to make it look pretty. So first off, we should get the file. So in this exercise, we're going to load it from our Allotrope Perl server, but of course, in the real world, you could load this from a REST endpoint. You could pull it out of S3, an Amazon data share, or any other file or Perl server, or anywhere really. It's just a file. So we'll just go ahead and pull this down, and Corey's nice little piece of code means that it presents this JSON file in a nice, fairly easily readable way. We can kind of expand it out and just take a look at the data. So I've opened it up a little bit. We have a liquid chromatography aggregate document. It holds a document, or some structure to provide a framework for storing all this information. The interesting bits is probably things like the sample document. We have underneath that, we have a sample identifier and a written name. So it's sample 1. We know that the analyst is JMR 38889. We have an injection document underneath that, which tells us information about the injection, the volume setting. So in this case, the injection was 5 cubic millimeters. The injection time's given there. So this was a 2016 example. We have information about the detector control settings. So in this particular example, we have 2 detector control documents. One of them is a single channel, and the other one, if I open it up, is UV spectrum. So it allows storing of this kind of different kinds of detections, different kinds of data sets, and all of these sort of settings can easily be stored. Again, this is all in line with our existing tabular model for liquid chromatography. It's just translated into an easy to read JSON format that hopefully looks pretty familiar for anyone who knows a bit about chromatography, it doesn't look particularly scary. At least that I hope not. So again, it's standard JSON. I didn't have to load any special packages or anything beyond sort of very standard kit. Nothing Allotrope specific to pull this down and read it and represent it in a nice, easy way of understanding it. So we have some liquid chromatography data. That's great. How about we plot the chromatogram? Oh, I forgot to mention, yes, as well as all of this information here, the measurement document, we have the peak list and all the peaks, all this kind of data, and the one that's probably more relevant right now because we're about to use it is the data cube. So we have the chromatogram. It includes information on the structure, as Amnon mentioned. So it describes that what you're measuring is absorbance in milliabsorbance units, and you're measuring it against time, acquisition time in seconds, and I'll open it up once. It'll take a little bit of time because it is 36,000 entries, but it's the data. Here's the raw data right there. So you have the full chromatogram in the file. So if we have it, let's plot it. So again, we have a nice bit of code here, and immediately it pings it into a nice picture of a chromatogram. At least I assume it's a nice chromatogram. I have no idea what's being measured. I'm not a chromatographer, but it looks like a chromatogram to me. So it's also using this. So this plot is using pandas, which again, folks who use Python for data science will probably recognize that as a very common data science package in this context. So this data is with very little work. Pandas data frame, you can immediately do some data science wizardry if you so wanted. In fact, most of the code that's on the screen here is not loading this data, it's making the labels correct based on the data set. So I spent more time putting together the labels than I did actually loading this into pandas. It really is that simple to work with. So we have the chromatogram. That's great if you want to work with the raw data. Easy. How about the peak table? So let's go ahead and do that, because most of the time you probably don't need the chromatogram. What you want is the peak table, and there it is. So in a nice pandas data frame, again printed out as a table, we've got 3 peaks. They have peak areas, they have retention times, they have the units, and all the good stuff's there. So in really not very much code, not very much effort at all, we've got data, and more to the point, data in a nice, easily accessible format that people can just go ahead and work with in using standard existing tools, pandas to do data science, or if you're doing something else, it's similarly easy to just load this in and do whatever you want to do with it. So we can load an ASM file pretty easily. We can read it and plot it pretty easily. The other step that Amnon mentioned earlier is validation. So we want to make sure that the data is correct. We don't want to be doing data science on bad data. So how about we validate it? So that's fine. That's easy, and we'll show you how to do that too. First off, we have to pull the ASM manifest. As Amnon mentioned, there's one key attribute in the data, which is the ASM manifest. What that does is basically it's just a small file that tells you, as he said, where the JSON schema can be grabbed from, what version of the ontology was used, what version of the shapes used. Most of this we don't need, but we do need to grab the schemas. So to do that, we need to grab the ASM manifest. And a key note, because this is something that we've hit for those that are interested in doing this, the code does this, but just in case you're writing your own code, you do need to send a request for JSON in the HTTP accept header when you request this, because if you don't specify, it will return turtle by default. That's just an artifact of how the Perl server was originally set up. Turtle is the default, and because there are 2 files identically named, the default is to pick turtle. Again, for those who are following along at home, the code already does this, but just in case anyone goes and writes this, that's something you might want to be aware of. Again, not particularly difficult to do. Very small piece of code here, and again, this half of this is just making sure that the right header's in place. But if we pull this down, we get a manifest, again pulled straight from the Allotrope Perl servers. It lists the vocabulary, it lists the shapes, which we're not so interested in right now. And the main thing that we really care about is it lists the JSON schemas. So here's the link to the JSON schema that we're going to want to use. It pulls down the deconvoluted, the deconstructed version, not the embedded version, but that's fine. That's all we need right now because we have a well, because the package that Python uses actually deals with the references for us. So we'll stick with that one just to make it a bit easier to look at. So we pull down the manifest. We have a link to our schema. We can go ahead and pull that down now. Pull down the wrong cell. So if we go ahead and pull that schema from the file that we just got, it pulls down a JSON schema. Now this bit's probably going to look a bit more scary for those who aren't particularly familiar with JSON schema. Fortunately, for the use case that we're talking about here, for people who are doing sort of data scientists, sort of like people who are working just working with data in the lab, you don't need to understand or worry about this. You just need to be able to grab it and load it into your validator. It just works. This is the sort of secret sauce, as it were. You don't need to worry where it's coming from. Just pull it down and validate with it. That's where we come in to produce all of this. So again, for those who are comfortable with JSON schema, it probably doesn't look so bad. But again, your average data scientist doesn't need to look at this at all. You just pull it down. So we can go ahead and pull that down, and now we can use that to check that the data is correct. So we have the data, we've pulled it down earlier, we have the schema, we've just pulled that down. So let's go ahead and make sure that the data is actually valid. So we run that and the data is valid. Great. I'd hope the data is valid given it's our example code. But of course, we can say it's valid. That doesn't prove it's valid. Someone could just say, right, data is valid. That it's not a very convincing demo, unless you actually show that it doesn't work when it shouldn't work. So let's go ahead and break some things, make sure that it catches them. So we had a pump model number in the earlier file that's a string. It's G7112B or something like that. How about we change that to a number? So then it's the wrong data type. So let's go ahead and try that and then validate it again. So it used to be 7112B, now it's 123456. And oh look, it's the wrong type. It's not a string. So the schema is not happy. We get a validation error. So if you're creating data that's wrong, has the wrong data type, it will tell you. How about if we give something the wrong unit? Because data types, it's an easy mistake to make, and sometimes an easy mistake to catch. But wrong unit, that's a little harder for a machine to understand, perhaps. So let's go ahead and try that. So we make a peak area unit seconds instead of milliabsorbent units times seconds. So go ahead and change that. So the old peak area was milliabsorbent units, now it's seconds, and what do you know? It doesn't like that either. So the unit is wrong. It tells you exactly where it is. The peaks list, peak items. So you can find, with a little bit of effort, again, it helps when you refer back to the file, but you can find where the issue is and identify that, peak 0 had it wrong, effectively. So great, we can check that the units are correct, we can check that the types are correct. How about if we remove something that's important? So without sample identifier, you can't associate this data with what you're trying to measure. So sample identifier is a mandatory field in this. Let's take it out. So we go ahead and take it out. Used to have an identifier of 1938 41 41. Now it doesn't, and it's missing. It's a required property and it's not there. So again, the schemas work just like they did, just like they do on the Shackle version, on the ADM version with RDF. We can check, things are present, things are absent. We can check that the units are correct. We can check the types are correct. All of the stuff is automatically generated from the schema tooling that we have to push from the RDF version into JSON schema, and that applies to all of our tabular models. We have these translations, we have these schemas available. That's really all it takes. In this, we've just pulled down a file, we've read the data, plotted the chromatogram, the peak table, we've tested the validation and made sure that it fails, works when it works and fails when it fails. All in that 10 minutes. Easy. I can say it, but hopefully those who do data science or use Python are nodding and agreeing. Maybe those who don't, might look at it slightly more askance. But it really isn't as complicated as you may fear. It really is that easy. It's not hard. So The last piece, which is slightly less technology and slightly more talky, is so we've read the data, we've plotted the results, and we've validated whether it's right or wrong. The last piece, how do you find what the terms are and what the terms mean? And again, this is harking back a little bit to the talk I gave yesterday, and to sort of one of Amnon's earlier comments. If you're looking up terms, probably the easiest thing to do right now is to go to BioPortal, because all of these keys in the ASM file are the preferred labels from our ontology. You can just put them straight into the BioPortal search. Go to the AFO page on BioPortal, jump to the term, the key in the file, and it'll plop you right out at the right term in the ontology, with all of the details on the right hand side of the page about what the definition is, what the parent is, what that unique IRI is. All of these things should pop straight out from that. It's going to be by far the easiest way to take this file and look up anything that you're not sure of. If you're not quite sure if the term definition is exactly what you thought it was, or maybe the term wasn't quite how you thought it was, but we use preferred labels, but we also have synonyms, alt labels, to sort of say other people call it this. Maybe the term wasn't exactly what you thought it was, but you can see that your term is in the old label, then it's probably the right term you're after, and we just have a slightly different way of naming it in order to make sure that it's consistent and correct across all of our files and all of our techniques. So BioPortal, to basically find what the terms mean, is going to be one of the easiest ways to work. Of course, now we have the term dictionary, that may be an option, but as that's still in beta, we haven't included that in this file yet. We may update that as that becomes sort of a fully finished and polished product. So yeah, hopefully in that sort of 10-ish minutes stint, I've shown you that it's pretty easy to work with Allotrope Simple Model. It doesn't take much in the way of code, doesn't really take much in the way of sort of specialist skills. I mean, if you know a little bit about Python, a little bit about data science, and you've ever worked with a computer, pretty much, you can just pull this in and run it. It's really as simple as that. So, and with that, I think that's about it. So, any questions?
So actually, Ben, while you were talking, I retested it on the Google Colab environment, and it's a fully working version. So there is no need even for a workstation, just for a browser.
Even better. So yeah, you can load it into Google Colab and not have a local copy of Anaconda and Python. It really is a very low bar to get started. And this is just the Python example. Of course, you can use JSON in any language. It just shows how easy it is to get started. And for context, I'm not a Python developer. As I said before, Corey had to do a lot of cleanup and making things look pretty. But putting this together took half a day, and most of that was understanding how Python works. It's really, really easy to work with. The JSON is a very common format, and every language has libraries, and it's pretty easily structured to find what you want. So yeah.
Yeah, there's a question in the chat window. I don't know if you
Yep, I see it. So Christian asks, thanks Ben for the live demo. ASM indeed looks very promising for our work in Python too. How do we actually get the ASM files? That's question one. And then two is there an ADF to ASM converter available already? So why don't we answer question one first?
Great. So getting the ASM files, it actually refers back to Amnon's talk earlier about looking into the GitLab repository. So the GitLab repositories have all of our models, which include the ASMs now. If you're looking for an instance file specifically, those are stored under the test folder. So we have GitLab, we have Perl and subfolders, and then we have a test folder. Underneath that, underneath that, you'll have the specific techniques, chromatography, conductivity, blood gas analysis, and so forth. And then underneath that, as you mentioned, the different maturity levels. Always go for the newest maturity level, obviously, because you're getting the very latest version. But at the bottom of that chain of folders, what you will find is technique name.json alongside the existing RDF versions of technique.adf and technique.ttl. So that's your instance artifact. The JSON schemas against that are in the JSON schema folder at that top level, and again follow the trail all the way down, conductivity 2021 12 rec and so on and so forth. Hopefully that answers where to find them, and I see Corey's already put the link to the GitLab repository in Perl. As for the ADF to ASM converter, we do have a tool that converts between ADF and ASM. Yes, that was part of the specification for the RFP. We wanted to make sure that bidirectional conversion was in fact correct and valid. So we do have a tool for that. I've got to double check what our release status on that is. I think it's in one of the accessible repositories, but I wouldn't swear to it, so I'd have to double check on that. But the intent is that yes, we will make that available. It does have a couple of caveats in that it's an automated translation for about 95% of our models, but there are a couple of edge cases that it cannot handle. So there are currently 2 models that it doesn't fully translate correctly. We can translate them, but there are manual steps at the end, which we have documentation for. So that converter is available. If it's not available to the community, it will be very shortly, but it is working and ready. So hopefully that answers that question too.
So I think for that one, I might have misspoke, but Christian was asking about converting here's where I misspoke, ADF, the Allotrope data format, to the JSON Allotrope Simple Models. So
yes,
you just talked briefly on that aspect, right, of converting the different data instances.
That was what I was talking about. We have a tool to convert ADF files, data files, as in, here is a chromatography experiment result from ADF into ASM. But you're right, I should clarify, because ASM is built on the tabular models, this tool only applies for data in a tabular model form, and specifically an Allotrope tabular model form. So for example, models which are in the graph form, so some of our LCUV examples, the mass spec examples, they do not have they cannot be converted into an ASM at this point because the models are different, and so the translation does not work. It only works for the tabular models. But yes, in terms of converting ADF files into ASMs and back, that is now possible through that tooling.
Great. Thank you.